All right, good morning everybody. We are taking a look today at the length along an arc. Welcome back to Mr. Grigoris Math, and in this video we're going to derive, yes, haha, the formula for, I know that's an awful joke. I'll cut, I won't cut that out or this, I digress. We're going to derive the formula for the length along an arc, and of course I'm not talking about that kind of arc. This would actually be totally applicable to finding the length along a circle. So remember earlier on in the course, maybe you had like a sector carved out like this, and it went through an angle theta, and you knew the radius of this particular sector. Then you could say the length of this portion from here to here was the length of an arc, and we had a simple formula for it. It was r theta. So not this type of arc. What happens if we have something that's non-circular? So this works because a circle is quite nice, but let's go with something that doesn't necessarily look or act or feel exactly like a circle as well too. So the length along an arc of a function can be found by extending, well, who does all the work in measurement and math? The Pythagoreans. Of course, there's many people throwing their pencils or chalk or whatever at their computer screen right now, because clearly it's not just the Pythagoreans doing work with measurement, but they did a heck of a lot. So the length along the arc of a function, and I suppose we need to draw a function at this particular point. So I'm going to draw a function here. My y-axis. There's my x-axis, and just for simplicity, I'm sticking in the first quadrant, and I'm going to just draw a generic function in green. So my function is going to look like, maybe I'll do a logarithmic function. That looks like fun. I think I did a logarithmic one last time. I'll do an exponential function. So there we go. That's f of x, and we're going to say it's equal to, I don't know, I guess we'll go with 1/4 e to the x plus 3/4. Just so that way this happens to be nicely at 1, so we're not too concerned about our y-intercept. Although it didn't really matter. This is entirely arbitrary. I didn't actually need a name for this particular function. Okay. So what if I want to know the length along this function from some arbitrary point to some other point? Like maybe I want to know, okay, how long is this section from here to here? So I can figure out very easily the area underneath this section by integrating. And I can figure out very easily the length of any tangent on this section by deriving. That's not my question. My question is, how long is this segment? So from this point, let's go from A to B. How long, following the curve, is that section of the graph? Well, to do this, we have to, much like we did with integration, break our curve up into smaller and smaller and smaller pieces. So I'm going to zoom in just on a section of this, and actually I'm going to zoom in twice, and actually I'm going to zoom in 3 times. So I'm going to really, really super zoom in. And if you remember from calculus when we were dealing with a series of shrinking secants, as we brought those secants closer and closer and closer and closer and closer together, as we drew the picture bigger and bigger and bigger, this region that's zoomed in is going to look even flatter. It kind of looks kind of flat right now. But then as I zoom in even more, it's going to look even flatter. And as I zoom in even more, it's going to look even flatter. So we'll take this triple zoom and we'll draw it over here. So I think it's going to look kind of like this. Now this is not a straight line. This is still determined by this function, but it looks an awful lot like a straight line. And let's say I've zoomed down to like the differential scale. So I'm now zooming at that scale of every unit across is a unit of dx. So if I consider from here to here, now you can see where the Pythagoreans are coming in. This is the measure dx for that very small change in x. Of course, what's the vertical measure going to be? Well, that's simply going to be dy. I wonder how I'm going to be able to use this somehow. Well, I think because I have a right triangle, because x and y are orthogonal to each other, a great basis for my plane, I can find this side length right here. Now, this isn't my full side length, but it's a portion of my side length. Now, we know from the Pythagorean theorem that this is going to be the square root of, let's just do dx squared plus dy squared. So that's the length of that piece. And that is just, of course, this little tiny, tiny piece right in there. And I've obviously drawn it way too big inside here, because if we're at the differential scale, it's infinitesimally small. So I know an infinitesimally small length in there, or at least a way to figure out that small length. But I want to know this whole length from here to here. Well, I suppose what I need to do then is I actually need to add up all of these things. So how do I add up infinitely many continuous things? Well, that's with an integral. So I'm going to perform an integration from here to here of my length. Let's take a look at how that goes. So I am going to erase a portion of this, but not the whole thing. So we integrate to add or sum the continuous. I'm going to call them hypotenae, and I'm going to spell continuous correctly. Calling them hypotenae because I'm going to have infinitely many hypotenuses, and I just feel like hypotenae sounds better. So my length, which I'll call capital L, is going to be the integral from a to b, from here to here, of all of my hypotenae. So that's dx squared plus dy squared. But of course, that's not a very good integral for me to evaluate. I don't actually have anything out here. So I have no binds. I don't know which variable I'm integrating with respect to. And actually, I can integrate with respect to any variable. I think it's going to make most sense to integrate with respect to x, because my function is given with respect to x, or my function given with respect to y, and I had it written a different way. Perhaps I would integrate with respect to y. So I need to find a way to get the differential operator, the dx, out here. So I'm just going to erase a little bit more of my picture. And I'm going to try to take one of these dx's out. And I think the best way to do it is to, on my next step, kind of like when I'm proving my composite angle theorems for tangent, I'm going to divide through everything by dx squared. Now, of course, I've just divided denominators by dx squared, which means I also have to multiply the numerators by dx squared. And then this radical can be applied to this dx squared. And I have to erase more and more of my picture, and I apologize for that. So this is going to be b, the integral from a to b, of dx, dx squared over dx squared. I think that's just nice and simple and just goes to 1. Then plus dy squared over dx squared. Well, I'm just going to write that like this for now. dy dx squared. And this dx squared is going to come out of the radical. So this will be dx. So I now have a formula for length. Dy dx. That's in Leibniz notation, but we have another term for dy dx. Think that when we switch over to function notation, we would call that f prime of x, absolutely. So this is going to be the integral from a to b of the square root of 1 plus the derivative squared dx. That seems like a nice, simple little formula. Now, I caution you, this is an incredibly challenging integral to figure out in many cases. Probably the first thing people want to do with this is they say, I'd love to find the length along a parabola. Because I always knew kind of the distance between the roots, or the maximum height, so that's the distance from your roots to your vertex in whichever direction you're talking about. But I didn't really feel like it was done because I didn't know the length along the curve. Well, this can help you find the length along the curve. In fact, this will find the length along the curve. But it is a very challenging integral to perform, and it's because it has a radical and another expression squared underneath. So you're going to need a special type of substitution. Now, because it looks a lot like Pythagorean theorem, 1 plus something squared, because it came from Pythagorean theorem, we're very likely going to have to do a substitution with something that the Pythagoreans are quite involved in. I don't know, like a trig substitution. So it's likely that when we perform this integration, that unless it's a particularly neat or nice function, it's probably going to require us to use a trig substitution. Hence, in most cases, you'll have a calculator in hand, and this is a pretty easy thing to type into our calculator. So I'm going to coach us through on how to do that here in a second. Now, we have a function that we used to derive this original picture, and we had arbitrary values a and b. Let's pick some values for our arbitrary values in our example here. So, example. Find the length along f of x equals, I believe it was 1/4 e to the x plus 3/4 from, and let's just go with x equals 2 to x equals 10. So from 2 to 10, by the way, it's definitely going to be longer than 8. Like the shortest possible line segment you can have that connects 2 to 10 is going to be 8. Now it would be with a perfectly horizontal line. Now I'm going to write out the formula, and then I'm going to borrow a calculator, and I'm going to show you how to type this in on your calculator. So I'm looking for the length along a particular function. That means I'm going to use my arc length formula. Those of you wondering for your test, remember the arc length formula is simply not in your data booklet. So this would be one that I would probably try to remember or know how to derive it. Fortunately, it's not too complicated. Now, I need to know my values of A. Oh, well, that's 2. My value of B is going to be 10. But I need to take the derivative. So I'm going to go to my function, and I'm going to calculate the derivative. Fortunately, it's a pretty easy derivative. It's just 1/4 e to the x. So it's not a very challenging derivative for us to go ahead and substitute. So we'll go ahead and integrate from 2 to 8 of 1 plus 1/4 e to the x squared dx. Now, again, I had mentioned I'm not going to integrate this by hand. I'm just going to borrow a calculator. And that looks like an appropriate distance for the camera. Yeah, there we go. So I'm going to do two things. I think first I'm going to go to my y equals and clear them out. And I'm actually going to plot my original function. So this is going to be alpha, it'll be 1/4 e plus 3/4 and I'll just go to zoom standard so that we can see this thing. And you can see that it's forming a function that looks kind of similar to what I had drawn, although my scale is way off. Now, if I were trying to do this formula along here, I would have an issue. That's the reason why it's not on the calc list, because I'd have to make sure that I have the entire window open. Okay, now we'll go to second function quit, and we'll go to math 9 to bring up my integral. I'm going to go from 2 to 8, and I'm going to make sure I do the square root first. So this is 1 plus. Now, if I had a very complicated function and I didn't want to find the derivative, I could just type in the derivative rule here. So I'd used y equals to plot the entire function as y1. I can go math 8 for derivative, and I can actually take the derivative of my function. That was y1 with respect to x. And I have to remember to square that. So I hope that I've left enough room for the syntax to work on that. And then this is dx. So this might actually go ahead and do the calculation for me. Let's see. Perfect. I got 743.656. Now, I'm just going to verify. I'm just going to verify that trick that I did by typing in the derivative instead worked out well. So I'm going to copy my original line, and I'm going to go back to where I typed in my derivative, and I'll just delete that whole derivative expression, and I'll type in my actual derivative, which was just 1/4 e to the x squared. And I should be able to get to the exact same measure. So if you don't want to take the derivative of this function because perhaps it's a challenging derivative or you're in a rush, you can just use your calculator to effectively skip over and just substitute in the actual function and the derivative rule in your calculator right there. So how long is that line? It's pretty long. Now I know it didn't look as long on my diagram, but it's because my scale was really flattened. So had my scale been not so flattened, this line would have shot up very quickly because, as we know, exponents grow really long, really fast. So that is the use of a length formula to find the length along an arc that is bound by a function, not necessarily an arc of a circle. Now, earlier on, I had made a little hint about a question that I'd like to ask on an exam. So, might not be a bad idea to try to prove that on some interval we can go from 0 to 2 pi. So I think it'd be nice to be able to prove this length of an arc formula on some interval using the arc length formula. And just to give you a further idea of how I am planning on incorporating this type of question, get out your spoons, I suppose. If you recall toward the end of your step or your exam paper 2s and paper 1 part Bs, they had many step questions. So I might guide you first through the proof of the arc length formula, and then maybe an easy use of it. And then I would have to give you the arc length formula at this point so that way you could go ahead and verify and prove this. So I'll leave this up to you to try. I think it would be a fun one, kind of similar to when we did the volumes of revolutions and we proved the formula for the volume of a cone. I think you're going to find out that this works out quite nicely. Anyways, take good care, and we'll see you shortly. Oh, don't forget to hit like, subscribe, notify bell, ding, merch, all that jazz.